Milimo Video is a full-blown AI filmmaking studio that, get this, runs entirely on your own computer. But how is that even possible? Well, in this explainer, we're going to pop the hood and break down the core engineering challenges and the absolutely brilliant solutions that make it all tick.
So the vision behind Milimo is, let's be honest, incredibly ambitious. We're talking about a complete professional video editor that is local first. That means no cloud servers, no uploading your data, none of that. It's all about raw power, running right there on your machine and integrating the best of the best AI models, like LTX2 for video and Flux2 for images.
This, of course, raises a huge question. How do you possibly pack that much computational horsepower onto a single machine without it, melting? Well, the answer lies in some seriously clever engineering.
Okay, let's start with the biggest bottleneck for pretty much any local AI setup: memory. We're talking specifically about the VRAM on your graphics card. You've got these massive, hungry AI models all fighting for the same, very scarce resource. It's a real problem.
And this right here shows you just how big that fight is. LTX2 for video needs almost 76 gigabytes of VRAM. Flux2 for images, it wants another 36. And the large language model running on a Llama, that's almost 49 gigabytes. These are absolute titans of AI, all trying to cram onto a GPU that might only have 16, maybe 24 gigs. It's just not possible.
So the solution is, you don't run them all at once. The developers built what is essentially a GPU traffic cop. They call it the memory manager. As you can see here, it enforces one simple rule. Only one heavyweight model gets to be in the ring at a time. When you go to generate a video, the image model gets booted from memory. Then, when you want to make an image, the video model gets kicked right out. It's this beautiful, elegant dance of loading and unloading models just in the nick of time.
And the memory management gets even more clever than that. For the large language model, there's this one simple instruction: keep alive 0. This basically tells it to get out of memory the second it's done with its task. It's a tiny little detail, but it has a huge impact on keeping that precious VRAM free.
Okay, so we've solved the memory problem. Awesome. But that just leads us to a creative one. How do you generate a video that's longer than just a few seconds? This is what we'll call the continuity problem.
The problem really starts with this number right here, 121. That is the hard limit. It's the maximum number of frames the video model can spit out in one go. At 24 frames per second, that's just over 5 seconds of video. So how do you create a 10-second, a 30-second, or even a minute-long shot?
The solution is this really cool process called chained generation. It's basically a clever loop where the output of one step becomes the input for the next. As you can see, the system generates that first 5-second chunk, then it literally grabs the very last frame and uses that as the starting point for the next chunk. It just keeps doing this, stitching the pieces together and trimming a tiny overlap to make it look like one single continuous shot.
But the secret sauce, the thing that makes this whole process totally seamless, is a technique called quantum alignment. See, the AI doesn't think in individual pixels. It sees the world in these little 8x8 pixel blocks. To avoid any weird glitches or artifacts right at the seam where two video chunks connect, the overlap between them has to line up perfectly with this 8-pixel grid. It's a super technical detail, but it's absolutely crucial for creating flawless long-form video.
So generating the video is one thing, but a real studio needs a professional interface, right? This brings us to the third big challenge: building a high-performance timeline that runs at a silky smooth 60 frames per second.
For any creative tool, this is just non-negotiable. When you're dragging clips around or scrubbing through your footage, the interface absolutely cannot lag. It has to feel fluid, immediate, which means the code has to be incredibly efficient.
And to achieve this, the developers made a really key choice. Instead of trying to manually draw every single thing with something like HTML canvas, they used standard web elements. This basically lets them leverage the browser's own highly optimized rendering engine, which is almost always faster and way easier to manage.
This slide shows that whole philosophy in action. See, the slow way to move a clip on the screen is with the left property. That makes the CPU recalculate the whole page layout. But the fast way, which Milimo uses, is with transform. This seemingly simple change offloads all that animation work to the GPU, giving you a much smoother hardware-accelerated experience. It's night and day.
All right, so we've got our core AI and a responsive UI, but what about all those advanced, intelligent editing features? Well, this brings us to our final challenge: adding an intelligence layer without completely destabilizing the entire application.
For those next-gen features like in-painting or rotoscoping with a click, you need another model. In this case, it's SAM3, the Segment Anything model. But hold on, as we've already seen, our GPU VRAM is completely packed. So how do you possibly squeeze in yet another resource-hungry AI?
The answer is, you don't. You don't add it to the main application at all. You run it as a separate, what's called a decoupled microservice. This table traces the process perfectly. The user clicks. That request goes to the main backend, which then just forwards it along to the SAM3 service. SAM3 does its thing, returns the mask, and then the main backend can perform the in-painting. This totally isolates the process, which prevents memory conflicts and makes the whole system way more stable.
So when we put all these pieces together, it becomes really clear that this isn't just a collection of clever hacks. It is a very carefully engineered system, all built around a single cohesive vision.
I mean, what we've really seen is a symphony of solutions. You've got the memory manager acting as that VRAM traffic cop. You have quantum alignment, which overcomes the model's physical limits. You have smart CSS choices delivering a truly professional user experience, and a decoupled microservice that adds powerful intelligence without compromising stability. Each one is just an elegant solution to a really critical problem. And this really leaves us with a final thought. We've just seen the incredible engineering that was required to build this kind of tool today. So as that engineering gets more common, and as local AI becomes the standard, you just have to wonder, what creative barriers that seem impossible to us right now will be the very next to fall?